So, good morning, everyone. Today we will learn about image compression. So, what is image compression? Image compression is nothing but reducing the size of the image. Size of the image. Okay. This is the basic definition of image compression. So, how we reduce the size? How we perform compression? How we perform compression means how we reduce the size of the image. So the first one is by removing the repeated information. Okay, or by removing the unwanted information. Unwanted information. Okay, so the repeated information is known as redundancy. Okay, redundancy. Okay, so why we need compression? Why we need compression? So first one is for transmission purpose. For transmission purpose. Because, for example, consider if your net speed is 15 kbps. Okay, 15 kbps means it can transfer 15 kb per second. Okay, if you have 1 GB file. Okay, 1 GB file. How much time it takes to transfer? How much time it takes to transfer? Hmm? So 15 kb, 1 GB means 1024 MB. So 1024 into 1024 kb. Okay, per second. So 15 kb per second means divided by 15 is equal to your time. So it takes minimum 2 to 3 hours time to transmit this file. Okay, because in olden days mostly 15 kbps means high speed data. Nowadays we getting 1 GB or 2 GB speed, but olden days maximum speed is 15 kbps, very less, mostly in kbps only. So to transfer a file it takes more time. So for that purpose, the compression technique is introduced. Second one is for storage purpose. Okay, storage purpose. Okay, so this is the basics of image compression. Now, after performing compression, how can we judge the quality of the compression? Quality or analysis of compression. Quality or analysis of compression, whether the compression is best or not. Okay, it can be judged by using three parameters. First one is compression ratio. Compression ratio. So compression ratio means it is a ratio of number of bits by in two representations. Okay, so B means number of bits before compression. B dash means number of bits after compression. Okay. So the B and B dash means representation of same image in two notations. Okay. So we can use either number of bits or L average or size of the image, because size of the image is represented in terms of bits. Okay. L average means also it is a length of the bit, so it is also number of bits only. So we can calculate with respect to L average or the size of the image. So this is the first parameter to analyze the compression is best or not. And second parameter is redundancy. Redundancy is given as capital R is equal to 1 minus 1 by C. Okay. And one more parameter is bits per pixels. Bits per pixels. BPP means number of bits by number of pixels in the image. Okay. Number of bits by number of pixels. These are the three important parameters to judge the quality of the compression techniques. Quality of the compression techniques. Okay. Next to important technique, important judges is fidelity criteria. Fidelity criteria. It is also important parameter which judges the quality of the image. Which judges the quality of the image. In fidelity criteria, we judge the images based on the loss of information. Okay. Loss of information. In terms of loss of information, we judge the quality of the image. Okay. So the fidelity criteria is classified into two ways: subjective and objective. So subjective means based on observation, we judge the loss of information. Okay, we judge the loss of information by rating, by providing rating. Objective means by calculating the error between compressed image and original image. So it is mathematical analysis. This is theoretical analysis. Mathematical analysis and theoretical analysis. So in subjective criteria, we have to according to the TASO. TASO means television industry, okay, standard organization. Okay, they give some standard ratings. So the ratings are start from 1, 2, 3, 4, 5, 6. Okay. So 1 means excellent. 2 means fine. 3 means possible. 4 means marginal. 5 means inferior. 6 means unusable. Okay, these are the basic ratings according to television standard organization. Okay, theoretical ratings. In objective type, we calculate the error. So error is given as E of x comma y is equal to compressed image f cap of x comma y minus f of x comma y, where f cap is compressed image, f is original image. Compressed image, f is original image. Okay, and through the error we can calculate mean square error or anything, or SNR ratio. Okay, this is the fidelity criteria. Next, redundancies. I said already, redundancy means repeated information. Okay, so the redundancies are mainly classified into 3 types: coding redundancy, interpixel redundancy, and third one is psychovisual redundancy. Okay, psychovisual redundancy. So let us see the coding redundancy. Coding redundancy means generally each pixel is represented in code words. Okay, in code word, some binary representation. Suppose, for example, I am considering 4-bit image. 4-bit image means we have binary values from 0 to 15, means 000 to 111. Okay, 00100011 0100 0101 0110 0111 100 1001 1101 1101. Okay, so we have 16 pixels possible value. Suppose I given one image like this: 11456. Sorry, 230123. Okay, 12367 46, like this I given. Okay, have you observed here the maximum value is 6, right? The maximum value is 6. So 6 binary value is 0110. 0110. So observe here. So to represent 6, we no need to require 4 bits. 3 bits are enough. 3 bits are enough. If you remove last bit, there is no loss of information, right? There is no loss of information, but bits are reduced. Bits are reduced. How many bits? 1 bit is reduced. but there is no loss of information. So this extra bit is called coding redundancy. That extra bit is called coding redundancy. So to remove the coding redundancies, to remove the coding redundancy, we use encoders. Okay, encoders. So encoders are many types. Some of examples are Huffman coding. Okay, Huffman bit plane coding. Okay, variable variable length coding. Okay, so many encoders are there. Encoder which removes the coding redundancies. If you want to get back original image once again, we use decoders. Okay, we use decoder. It is the reverse of encoder. Reverse of encoder. Okay. So next is interpixel redundancies. Interpixel redundancies. So generally, if you make so many pictures at a time, if you take pictures, snaps at a time, or if you take the screenshots from the video sequences, the information mostly the information available is mostly replicated data. Replicated data. Okay. Have you observed? I think you all observed. So while capturing multiple pictures, or mostly the information is replicated. Okay, in video sequences also. Okay, so mean the data is replicated due to the correlated pixels. Due to the correlated pixels with respect to the space and time, because space means 2D images. Okay, 2D images. With respect to time means video. Okay, video sequences. So spatially and temporally means with respect to time. Okay, image pixels are correlated. So due to this, more information is replicated. More information is replicated. Okay, more information is replicated. So this type of replicated information is called interpixel redundancies. Interpixel redundancies. So it is also known as spatial and temporal redundancy, because the pixels are correlated with respect to space and time. Space and time. So we call it as interpixel redundancy, or spatial and temporal redundancy. So removal method of spatial and temporal redundancy is mapper. Okay. So mapper will perform non-visual transformations. Non-visual transformation between the pixels. So for example, we use run length coding. Okay. Run length coding is one type of the mapper. So next redundancies is psychovisual redundancies. So the reverse process of mapper is inverse mapper. Inverse mapper. So here also we get original image. Here also we get original image after compression. Next, psychovisual redundancy. So human vision is involved in these redundancies. Human vision is involved here. So intentionally human will neglect the information. Example is cropping. Okay, you can crop some information, right, and transmit the information. Okay, cropping of images, right? This is one type of redundancy, psychovisual redundancy. Intentionally human will neglect the information in the image. Okay, so this information is also known as irrelevant information. Intentionally we neglecting the information. So the removal method is quantizer. The removal method is quantizer, and it is irreversible process. It is irreversible process. Okay, means we don't have inverse quantizer. Okay, we have only quantizer. The process is irreversible. When you are apply quantizer to image, information is lost. We don't get back the original image after compression. Okay, so these three are basic redundancy types. What are those? Coding, interpixel, and psychovisual redundancies. So if you remove these three redundancies, image get compressed. Okay, image get compressed. So the basic image compression model is given as follows. So the basic compression model is given as follows. So first one is encoder, input image, encoder. Next, encoder will remove coding redundancy. So interpixel redundancy is removed using mapper, and psychovisual redundancy is removed using quantizer. So after applying these three blocks, we get compressed image, right? Compressed image, and then we transmit the image, and then we transmit the image, transmit the image. So after transmission, the receiver received it, and he want original image. Then there is no reverse process quantizer, so we neglect it. So mapper, the reverse process is inverse mapper, inverse mapper. Next, encoder reverse process is decoder. Okay, so that we get decompressed image. We get decompressed image. Okay, this is the basic image compression model. So the basic image compression model we can classify into two ways: lossless or error-free compression and lossy compression. So lossless compression means we not use quantizer block. No quantizer block is available because using quantizer the information is getting lost. So we can't get back the original image. So the basic block diagram is encoder, mapper, this transmission, and then inverse mapper, this is channel, transmission channel. After inverse mapper we use decoder. This is decompressed image. Input image. Here compressed image. Okay. So lossy compression means here we include quantizer block also. Encoder, mapper, quantizer, next channel, inverse mapper, and decoder. Okay, this is the basic image compression model, lossless and lossy.